Hello, everyone. My name is Matteo Salvarezza. I am a developer in the machine learning team at Wolfram Research. And in this presentation, I will talk about current and future backends for the neural network framework. So this is the outline of the talk. I will talk about backends in the context of the main framework, backends in the context of net external object. Then I will talk how they will interact with each other and how they interact with accelerated hardware. And then I will talk about future backends. So one thing, I will keep an eye for questions throughout the presentation. So please put them in the Q&A section, and I will try to answer them as the presentation goes. And then at the end of the presentation, if there's still time, then it will be like 5 minutes for other questions. Okay, so backends and the neural net framework. So what do we mean by backends in this context? Well, the neural network framework in the Wolfram language relies on external code, which we call backends, to manage network evaluation and network training. So what does this mean? This means that backends are not used for anything that involves creating and manipulating network expressions. So, for example, in this code, when I create this net graph, this is our own backend agnostic expression, and there is our own code to manipulate these things. So whenever I create this expression, I can extract parts whenever I manipulate them by adding parts. Oh, would be nice if you could share the notebook. That's a good point. Is it too late to do it now? Probably is. Okay, I will make sure to share it after the presentation. So for all these cases, we are not using any backend. And also for like net encoders and net decoders, when we run them, so for example, here I'm encoding a random image, there is also in this case, there is no backend involved. On the other hand, backends are used when I feed an input to a network and get the result out. There is some computation happening. We get, and this computation is happening in the backend, and we get the result out of that. Same thing for vector passes. So when I feed an input and ask for network gradient computation is performed by backend, and same thing for training. There is a lot of like our functionality running around the backend for training, but at the core, like these evaluations happen in the backend. So, and basically, the idea is that when we need to use a backend, we take the internal representation of these networks and translate it to a form that the backend can understand, and ask the backend, "Can you please run this?" So. Just to show you what this is, like the internal underlying representation of network can be obtained by running this function, this internal function. So this is, you can see it's a net graph, this information about the inputs, information about the outputs, and information about all the layers with all the weights and the parameters and everything. So we take this entire thing and we need to translate it to a form that the backend can understand. Okay, so now, the other side of the story is net external object. So net external object is sort of a satellite of the framework, and it is just a thin wrapper over a network which is managed directly by the backend. So they can normally just be constructed by importing a file, and the file has to be in a file format associated to the backend. And the backend used is already declared explicitly in the object. So with this statement, I can import an ONNX model in net external object as net external object, and you will see here like this is the ONNX runtime logo, which is the backend that is responsible for running this model. And you can see also format logo, it says ONNX. We also support MXNet in net external object, so this is a net external object that's managed by MXNet. And notice, like when I click plus here, I don't see any internal structure of the network. And this is by design. Like I'm not seeing which layers are there and what they do and what are their parameters, okay? This is happening for nets that are managed by the framework. These nets are not managed by the framework. They're managed by the backend. So they're treated as black boxes. So there is no access to their internal structure. And also, I should mention, there is no, at least at the moment, you cannot train these objects nor compute gradients with them. So obviously, running these objects obviously triggers the backend. So when I run this statement, I run the net external object on input. This computation has just happened on its runtime. So yeah, doesn't support gradient computation, and so the idea is was basically to create a thin, as I said before, a thin wrapper over the external library to enable easy use of external pre-trained networks. So if you have a model which is in a file format of another backend, you can use net external objects to use it if net external objects supports this backend. At the moment there is just two, but it was designed to be like extensible, so we can add backends to this pretty easily comparatively. So in this case, there is no translation from our representation to the backend because this object is already like only exists in the backend format. It's not being translated from our expression. Okay, let's talk about accelerated hardware now and sort of like putting all these two things together. So this is a picture of, oh, I should make this bigger, sorry. Okay, this is, oh, let me just go through, okay, like this. So this describes the interaction between like top level objects, backends, and hardware. Or like this is, I mean, if we wanted to be pedantic, there should be another level here because there's like software backends and hardware. Anyway, there's two levels of software backends if you want. These are frameworks and these are libraries. Anyway, so both the framework and net external object can use both backends, and these new connections were added in 14.1. And you can see like the main the main new thing from this is essentially this path here, which finally allows the neural network framework to use hardware acceleration on Apple Silicon devices, which was something that was missing for a long time after Apple divorced from NVIDIA, and basically this path was made unavailable on Mac. There is also this DirectML, which is a library on Windows, which allows to run on integrated GPU. It also allows to run on NVIDIA GPUs, but you should really use CUDA for that. So there are lots of exceptions and caveats to this picture at the moment, and I will describe them. So, well, first of all, whatever goes to ONNX runtime cannot be used for training gradient computation. Okay. Net external object explicitly is tied to a backend because we've seen it reports the backend it's using, while the NM framework doesn't. The NM framework selects which backend to use for a given network dynamically, depending on what you put in the target device setting. And some examples are on Apple Silicon. If you go target device goes to Core ML, it uses ONNX runtime backend to access neural engine, so it goes this path. With DirectML on Windows, it uses ONNX runtime to access, so it's this path. But you can also go to an NVIDIA GPU if you want. It's not really recommended. You should use CUDA for that. In other cases, we go to MXNet. Then another complication, you might be familiar with target device goes to GPU. That is still a thing, but now this has become a meta setting that translates to either CUDA, DirectML, or CoreML, depending on the platform and available hardware. And you can check the documentation page of target device for a complete picture. So, like at the moment, this is quite complicated, too complicated. And like future goal is to make this picture more consistent and easier and more transparent. And in particular, I think we should we will expose a setting to control the backend from the framework directly instead of having it like being silently selected depending on just target device. So we will have like a device setting and a backend setting, probably. So yeah, and this will evolve, especially because future backends will be added, which is what I'm going to talk about now. At the moment, like this, like we have added this connection and these connections mainly to add this path and to give users the possibility to use other acceleration on Mac as soon as possible. But like this came with a cost in transparency, which we are aiming to now like settle. Okay, so let's talk about future backends. Now I can make this smaller again so I could see if there are questions. Okay. Now, generally speaking, adding backends to NetX and object is easy. Like it was designed to be that way. Okay, there is a question. Do you plan to add something for supporting the GPUs on x86 processor for use on Linux? I'm not aware of like any path to those, which doesn't mean there is no path to those, but it's something we have no plan for at the moment. So okay, will Trinium Command be available soon? It will definitely be available. Probably not through ONNX runtime, which is what I'm gonna discuss in the rest of the presentation. Can you say anything about how access the open neural engine will mean for WL users? Well, I mean, it just means that net evaluation will be faster in some cases. So you will need to try out some network with normal evaluation setting, which is target device goes to CPU, and then you can compare the timing with target device goes to kernel. And like in many cases, you should see an improvement. Okay, so adding backends to NetX and object is easy because it was designed to be like backend agnostic, and there is no explicit management that we have to do. We just have to link to the backend, take an imported model file, send it to the backend, and say, hey, can you please run this? So what we are targeting in the future is Llama CPP, which is like I'm working on it right now, and we are aiming for 14.2 support, which is a library for LLM evaluation, which is specialized in LLMs, and then TensorFlow. There's other couple of questions. Are there plans to use the Google TPU? Yes. Google TPU should come at some point, and yeah, I will. You will see by the end of the presentation. Do you have a preference for CUDA or Caramel with Mathematica? It highly well. At the moment, they are mutually exclusive options because Caramel is only available on Mac because Caramel it's only an Apple thing, and CUDA is not available on Mac. So if you are like if you don't have the freedom to pick your platform, you cannot make this choice. In general, it's very hard to say which one is better because it highly depends on if you have to change machine, it means you also have to change GPU. So you have to. It depends on what neural engine chip you have and what GPU you're comparing, and so like there's not a straightforward answer. In general, I would say CUDA is probably like more consistent support just because it's a much older thing. So, okay, adding backends to the NN framework is much harder because we have to we need to make this translation work for every layer to the backend. And manage the gradients and the optimizer for training and other things. Now, we are forced to do this switching because MXNet was retired, which means it's not getting any more feature. It's not getting any more bug fixes. It's not gonna work with like updated versions of CUDA. It's not going to support other accelerated library, like it's dead end. So, and ONNX runtime, which you already have in the system, is not a fully fledged neural network framework at the moment. It started just as an inference engine, so just for passes. They are moving towards supporting training, but they're not there yet, and still, yeah, it was not born as a fully fledged framework. So the plan is to eventually phase out MXNet and remove it from the system, which will take quite a long time, and migrate the NF framework to use one or more different backends. And the main candidates for this are PyTorch and TensorFlow, obviously, because they are like the dominant players in the landscape. So initially, we aimed for feature parity with the framework, which means basically users will not realize that anything has changed under the hood. And then we will start looking into like new functionality unlocked by the factors in the backend. And so to this purpose, in the last part of the presentation, I want to show you what I've started doing with PyTorch. So I am currently developing a link to PyTorch, which will be eventually, for which we will target hooking up to the main framework. So at the moment, this code is only available internally, so your builds do not have this, but it will get there at some point. It will never be like user exposed functionality. The end goal is just to get the main frameworks of like NetGraph, NetChain, those things, to use this thing. And last remark is that despite PyTorch containing the word Py, there is nothing done with Python in this project, because as every high performance deep learning framework, PyTorch uses C++ library under the hood, and we are directly using this library, so we are bypassing all the Python part. There are more questions. Yes. Do you support the AMX instruction set on Xeon workstation CPUs and your CPU backend? Well, we support whatever instruction set the backend supports. I am not familiar with this. So Xeon is Intel. We use an accelerated library from Intel. In MXNet already, which is called ONNX, and that should take care of. So the answer, like short answer is we support whatever our backends support essentially. And as far as Intel goes with ONNX, we have full support. So if something is there, we have it. I'm not sure like if there is something specific for this instruction set in ONNX. Okay, so let's see a little bit of PyTorch. So, well, the first ingredient for like all deep learning frameworks are the numerical arrays, and in PyTorch they're called tensors. So, like with this command, I have created a tensor in PyTorch, and I can read back data from it, getting a numeric array out of it, and yeah, and you can see that if there are no bugs, the output, the content is the same. Then we can run operators. So at the moment, like this is also like experimental syntax, like this is internal things are subject to change. At the moment, this is how it looks like. So there is PT operelu, so this matches this has to match the name of our PyTorch operator, and like these things will match the name of whatever you find in the documentation, in the Python API documentation of PyTorch. So we will be using the same names. And then also we can apply it to this tensor. We can get an output, which is another tensor. We can read from it, and you can see the negative numbers were set to 0 because that's what Relu does. Any plans to support use JAX? We will look into it. Yes, we will look into it. Okay, we can run a slightly more complicated operator. So linear, which takes 3 inputs, a data input, W, and a B tensor. bias tensor, so I can create these 3 tensor from this data. This time this takes 3 inputs, same thing gets me an output, and I can read it. And I can also compare the result with the linear layer here. So this is the equivalent thing. We're using weights goes to W, bias goes to B, and with critical input. And the two libraries again. So this result was computed in PyTorch. This result was computed in MXNet. There's another question. Given the Wolfram language ability to handle arrays, blah, 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 would you never consider building a native embedding of WR? The problem with that is gradients. Sure, like the kernel is very good at handling all those things, but it doesn't compute the derivatives of that. There is work with the Wolfram compiler, so there is like functionality which is in development to basically augment the kernel to get it to compute derivatives of those things in an efficient way with backpropagation and everything else. But using the Wolfram compiler, but it's not right there. Obviously, like in the language, you can also compute like you can also compute derivatives, like there is a B function, but that's not what you want to use for neural networks. Another question, I think, in terms of ONNX does support the MX instruction set extensions. I don't know if that work on AMD processors. Well, so yeah, I've never gone like in testing exactly like performance benefits of 1D and AMD versus Intel. What I know is that at least a subset of the optimization that 1D does are optimization for x86. So you should get those on AMD. Then maybe like I expect they, you know, on Intel they can leverage more things, but like I don't have like any concrete investigations on this. Okay, so let's move on to gradients, which I was just talking about. So the way you compute gradient in PyTorch, this like the feeling of using this interface is more or less like using the Python interface to PyTorch. So if you're familiar with that, you know about this requires that. The different thing is how we use the operators, because PyTorch has classes in Python, but we don't use those. We use like a functional approach, essentially. We directly hook up to the primitive because we don't need to use the classes for the operators. Anyway, data. I can create a PyTorch tensor, but this time I can turn on this flag, requires grab. I can then feed this operator, this tensor to an operator, get a tensor and output, but then since I have the set requires the true, I can run the backward pass on these outputs, which will fill out the gradients. Now, how do I get the gradient? Well, I can get the gradient associated to the input using this function. The gradient is another tensor, and I can read it, and this is what the gradient contains. And I can compare with just what I expect, because the gradient of the sign is the sign, and in fact, they match. So this time, this is what computed by PyTorch, and it was computed by the Wolfram kernel. Okay, a slightly more complicated case of evaluation. I'm going to be using Linux. Sorry if it's uninspiring, like every simple tutorial uses that. So, okay, I'm taking the pre-trained LeNet model from the neural network repository, and I'm extracting the arrays and converting them to PyTorch tensors. So now these are all the tensors that we need to use. Then I can create a function which basically runs the net in PyTorch. So this is a chain of layers. Right composition just means you run this one, then this one, then this one, then this one. So you can follow like this chain going from top to bottom. And I have taken care of setting all the parameters of the various layers. So this is a convolution, and you know, this is the correct padding size and strides and dilation and things which I've copied from here essentially. So like this is the kind of thing that hooking up the backend to the framework will compute automatically. Like it's all about going from something that looks like this to this. Now, for now, I did it by hand because that's yet to come. Okay, so we have this function that runs LeNet. You see, it uses the pre-trained arrays that I've created. So I can grab some image from MNIST. Let's grab a more interesting one. Well, this is a hard one, maybe. There are no net encoders and net decoders at this step. They are in the main framework. They're not in PyTorch link, so I have to encode it by hand. Then I'm creating a tensor using these, and I'm just running the net of the tensor, getting an output tensor. So these are the output tensor contains the probability values, and you can see that there is like 99.99% probability that it's a 7. So it's what. There's a new question. Will NetTrain be updated in 14.2? Well, it will support tabular. So yes, that's a small update. Okay. Well, I can compare with like the probability values from the main framework, so the one computed by ONNX. I just want to do it like I don't want to compare these numbers because this is like not very meaningful numbers. So we can remove the last layer, which is the softmax, and stick to the scores, which is what I've done here. And these are the scores look like for the class. And I can compute the same thing on ONNX, and you can see that the scores are matching. Another question. Are you considering developing an intermediate structural level consistent of evaluation like magic multiplication and element-wise ops to which an area can compile to? Yeah, this depends on like, whether we go for supporting multiple backends or not. Like obviously this is extra work, but it's work that pays off. So like it's a decision we have to take. If we decide to stick with only one backend because we find that like among all the possible choices we have, like PyTorch, TensorFlow, JAX, whatever. If we find that it's only one that really is really worth linking and that fit our needs, then maybe we don't do that. But if we find that there is benefits in having multiple backends, then we have to devise we have to design the best way to get multiple backends to work, and this might be one of those. Okay, last thing I can show is training. So, well, now instead of taking the pre-trained arrays, I'm just initializing the arrays using some settings. These are the variants for the nodal distribution for the weights. So I'm using random variate for the weights and constant array 0 for the biases because biases are always initialized to 0. And I can create again arrays for the net, but this time these are randomly initialized. And then the new thing is optimizer. So this is the object that takes care of reading the gradients associated to these tensors and updating them according to the gradients and the learning rate and everything. It's an object in PyTorch that we can create in this way. And you see there's some options with default values and everything. Let's get the training data. There's another question. There is an unrelated question about fourth-order differential equation that I have absolutely no idea about. Then there is, do you have any plans to support integrated neural processing units on access processor at Lunar Lake and Meteor Lake? Again, if they're integrated and they are on x86, that's one GNN job to use them. And I would assume that Intel has done the homework. Okay, so this is a function that computes that runs a training round. There are some technicalities here, but I am iterating over the batches, and I'm grabbing an input batch from the data, creating the tensor. I'm running the network on the input batch, then I'm running the loss function using the net output and the targets that I get from the data. These are minor technicalities. Basically, this is the forward pass, this is the backward pass, and this is PT optimizer step that uses the optimizer. So this is what uses the optimizer to read the data from the gradients and update the weights. It just looks like this because the optimizer was created by giving it a reference to the arrays, so it already knows which gradients it has to look for, and which arrays it has to update. Okay, so then there is progress reporting. This runs the validation loss, and it just runs the forward pass, and then it computes also the accuracy, nothing special here. And this is a training loop. So I'm training for 3 rounds on 200, the batch size 200. Now, this is not as fast as it should be, and I know part of the reason why. Obviously, like the time will come to make sure this is on point. At the moment, if you feel like it's not going fast enough, you're right, but don't worry, it will at the right time. So we're training for 3 rounds. It's 300 batches per round. It will take like maybe 1 minute. Okay, so after the first round, we have 91% accuracy, which is more or less what you expect. That's another question. Just to be clear, do you use 1DNN on Linux at this process? Yes. We use 1DNN on Linux and Windows. Yeah. In both, well, no, only in MXNet. So ONNX runtime has 1DNN support. It's there. You can do target device goes to 1DNN, but we chose not to expose it because it has several problems. And there are problems on ONNX runtime, on the ONNX runtime side. But like, if you feel adventurous, you can try to use it. On the MXNet side, it's enabled by default. So target device CPU, if you are on Linux and Windows, automatically uses 1DNN all the time. Okay, we're getting there. Then just have a few final remarks. We're done. Sorry for the slight delay. Okay, we're done. So, well, I have accumulated the information about the loss values. These are the similar plots that you see in the train. So this is batch loss on the training set and validation loss, and this is validation accuracy. So we end up with 95% accuracy after 2 rounds, which is what you expect. And here I'm just demonstrating that basically, and let's not spend too much time. It's classifying this correctly as a 1 with 98% probability. Okay, so final remarks. Well, future development, sorry. Now, next short-term goal is to add Llama CPP to net external object as a new backend. Then write a link to TensorFlow, which is going to be similar to this. Look into other options such as JAX, as someone mentioned. And then basically like try to make like to plan for what's going to happen as far as the main framework goes in the future. So at that point, we will have 2 links to the major libraries. We will have spent time looking into other options. So we'll have like a pretty good idea on what's out there and what we can do with it. So now then we need to strategize and see exactly what we should use in the framework. So comparing PyTorch and TensorFlow with others in order to access the strengths and weaknesses of possible backend. Possibly decide to use multiple backends. Then the same kind of like thinking, the same kind of steps can be taken from an external object, except it's much easier to add them. It's much less critical. There's not much planning one has to do. One can just add backends to it. So then, yeah, use the main backends in the main framework, phasing out on XNet, and then look into what's being allowed by them at the very last step. There's another question. On a system with an NVIDIA GPU and x86 processor, can the user choose to use either the NVIDIA GPU or 1DNN for the backend? Of course, target device. Target device goes to GPU. We'll use the NVIDIA GPU. You can set it to CUDA if you want to be more explicit, but GPU is going to be translated to CUDA essentially. Look in the target device doc page for details about that. And then you can select target device goes to CPU or nothing, because this is the default on all platforms. And it's going to use 1DNN. And this is for both net evaluation, so like this, or training, so net train, net data, target device. So they both work with CUDA, with 1DNN, with CPU, GPU. Okay, so presentation is over. We are 6 minutes over time. I guess like plenty of questions were asked, so there's probably no more questions. So yeah, thank you very much, everybody, and enjoy the rest of the conference.